Robert Andrews Millikan, most famously known for his oil drop experiment, was the first ever person to determine the magnitudinal charge of an electron, 1.6 times 10 to the 19 to be exact. As a scientist, Millikan made numerous momentous discoveries, chiefly in the fields of electricity, optics, and molecular physics. His record as a researcher and teacher was second to none. He was awarded a total of 25 honorary doctorates and many prestigious medals and awards, such as the Nobel Prize for Physics in 1923, which is no easy feat. His research on the electron was a critical factor in opening up the doors to the electronics revolution. We have set up an exclusive interview with Robert Millikan to further discuss more about his oil drop experiment. This interview was conducted via Zoom, so rest assured, social distancing was practiced. Welcome, Robert. Good to have you here.
Hello, thank you for having me.
Oh, it's our pleasure. Now, before we discuss the sciencey things, tell the viewers watching at home a little bit about yourself.
Well, I was born on March 22nd, 1868 in Morrison, Illinois. I had received my doctorate in physics from Columbia University in 1895. But fun fact, prior to developing my interest and love in physics, my favorite subjects were Greek and mathematics.
What about your family?
Yes, I am married to my beautiful wife Greta, and I have 3 wonderful boys whom I love very dearly.
Now on to the good stuff. How did you first come upon your discovery of the charge of an electron?
In 1897, J.J. Thomson discovered that atoms have electrons and electrons have negative charge with his cathode ray experiment. But he wasn't able to figure out how much negative charge electrons have because their charges are something that can come in different amounts.
And scientists wanted to figure out how much electric charge an electron had?
Yes, but you can't just take an atom and pull out an electron and measure its charge.
Right.
I was determined to figure out the charge of an electron. It wasn't until 12 years later that I had come across something revolutionary. What I did was I set up what was like a big chamber, and here is a cross-section of it. Over here is an atomizer. It's just like a perfume mister, except instead of spraying, perfume, it would spray oil into a tiny little droplets, and these droplets spray into this area. The droplets fall into a small hole in a charged metal plate, and there are 2 of these plates. The top one is positively charged and the bottom one is negatively charged, and they are both connected to an adjustable voltage source. When they fall into the main chamber, the air inside it is bombarded by this ionizing radiation. And the ionizing radiation, what it does is it basically strips the electrons off the air and lets the oil drops collect them as they enter the main chamber. And what you would see in the chamber when the experiment takes place is the drops of oil make their way into the hole. As they enter the hole, the more positive oil drops collect the more negative electrons that were discharged into the air by the ionizing radiation source. As the oil drops fall down due to the force of gravity, and if you turn up the voltage high enough, you'll actually observe the oil being suspended in mid-air. And what I also noted was that all the droplets were different sizes and didn't gain the same amount of electrons too, so we had to take that into account. To find the exact charge of an electron, I first had to determine the magnitudes of both the weight force and the electrical force acting on the oil droplet. So if the oil drop is suspended in midair, we know that the force due to gravity is equal to the electric field strength. So equate the 2 equations, F equals mg and F equals EQ, because the drop is suspended, then mg has to equal EQ. To find the electric field strength of the experiment, we can use another equation, E equals V on D, which equals the voltage applied divided by the distance between the 2 plates. By equating F equals mg, F equals EQ, and E equals VD, we get mg equals EQ, and then we sub in V on D, mg equals VQ on D, rearrange that, and then we get mgd equals VQ, and then we make Q the subject, Q equals mgd on V. So for each drop, the mass of it was measured, the acceleration due to gravity was known, distance between the plates were known, and the voltage applied was known. Therefore, we could find out Q, or the charge. And with that, I calculated the charges of various individual droplets and repeated this experiment hundreds and thousands of times and tabulated it. What I noticed was that every single charge had to have some multiple of 160 zeptocoulombs. So you figured out the lowest common multiple of the tabulated results. Yes, and this meant that this had to be the magnitudinal charge of an electron. And why was your discovery so important? Well, the electron was actually the first fundamental particle that we have confirmed the charge which helped us. Last and final question, why use oil and not water? That is a very good question. I previously tried water with this experiment, but what happened was that since the droplets were very small, they would evaporate under the heat of the light source when observed. A very special oil had to be used with a low vapor pressure point. Very smart. Well, that is all we have for today's segment. Please join us next week where we'll have another special guest, Albert Einstein, where we talk about his theory of general relativity.